this hour about section 5.3. Okay, and there are two main questions out of section 5.3. One of them is a question about what kinds of questions do integrals answer. So we've talked a little bit about an integral describes area, and in particular net area, area above the x-axis minus area below the x-axis. But how else can we interpret these integrals? It turns out there's a bajillion and one different ways to interpret these integrals, and today I'm going to tell you about a second one besides area. And then the next question is, okay, suppose that our function is not made up of straight lines and semicircles. How the heck do you evaluate one of these integrals and get an exact answer? And so we're going to talk about that today as well. Okay, so let's start with question number 1. And my first example, it turns out, actually doesn't have anything to do with an integral, at least not at first. And so in our first example, a particle is moving along a straight line with a constant velocity of 4 feet per second. Here's our question. How far has the particle traveled between time t is equal to 0 and t is equal to 3 seconds? So between 0 seconds and 3 seconds. All right, so take a minute, write that question down, and then think about it for a second. All right. Now I'd like you to talk to your neighbor a little bit and discuss how you would solve this, how you would answer this question. And not only how, but then what your answer might be.
Okay. Yeah, I mean, that looks but okay.
Send him on the phone.
I just talked to one of the 20 voices in my head.
Excellent. Odds are you get the right answer.
Yeah.
Well, because of time 1, it's gone 4 feet, right? Plus
Times 0?
Well, times 0, yeah, it's hasn't gone anywhere. Starting?
But that's music a second.
Right.
3 seconds.
Yeah.
It's, I think it's 12.
Does travel have 1 or 2 L's?
Travel.
What do you
I think it's one of those weird ones that have 1 or 2. All right, well today it has 2.
Yeah, right.
Okay, so on your discussions with your neighbor, did anybody come up with an answer?
Yes.
12.
Okay, 12. Do you guys agree with 12? Why do you say 12?
Because, especially with the examples we just did, and knowing that it's at a constant rate.
Wait, hold on, speak a little bit louder, Ben.
So, okay, I was just basing off of like what we had just discussed off of problem 30, what was it, 33? And using everything, I would set up the interval of like from 0 to 3 is along my x-axis and have feet per, or I guess feet as my y-axis.
Okay, so back up here.
Okay, sorry.
When you were thinking about this stuff, and you've now set up this entire integral, all this fancy stuff, anybody come up with, or did you do this any more simply than without an integral?
I just saw that, but I just set up a graph and just drew it, a rectangle.
Okay, so describe that again.
Okay, so knowing that we're going to have a graph, and I would set feet as my y-axis and seconds is my x-axis. I would have it going from 0 to 3 on my x and 0 to 4 on my y, and I just kind of draw the points together and do base times height, or half base times height.
Okay, so you came up with your final answer of 12 feet with that. Okay, all right, so you looked, so your thought bubble over here was you were thinking about something here with time in seconds along the and then you had something going on here, so from 0, and then you had a 3 over here, and then you had a 4 up here. Okay, you made some kind of a.
Because it was a constant velocity, so.
Okay, so this 4, so your y-axis here is velocity in feet per second. Okay. All right, so you did a picture something like that, looked at the area of that rectangle. Okay. All right, so the area of that rectangle, well, the width is 3 and the height is 4, and so this area is 12 under here. Okay. All right, other thoughts? Other Ben?
Velocity is distance divided, or sorry, distance is velocity times time. So we'll just.
Okay, so distance is equal to velocity times time. Okay, so distance is velocity times time. I'm going to put a little small asterisk on this. And so my first asterisk on here is distance is velocity times time as long as velocity is constant. Okay. All right, Jeff, you want to add to that?
Well, I agree with everything that's been said. The only thing the thought that occurred to me is that we're starting from 0 seconds. We already have a velocity of 4 feet per second, which then if you said, okay, what was the velocity of -1 second, can you have that? Or
So if
that's just a thought. I don't know what.
So maybe the question here is a question of how will this change if the question is between maybe t is equal to -1 second,
Right.
and t is equal to 3 seconds. And it's legit to talk about a negative time. Time is arbitrary. I mean, if we just say right now is time t equals 0, then a second ago, if we rewind, is t equals -1. So it's legitimate to talk about negative time. Okay, so I actually like both of these ideas that are up here. And so this idea of distance is equal to velocity times time, that's true as long as the velocity is constant. If your velocity is changing, then this formula doesn't work quite exactly. But here we have a constant velocity, so this is totally valid. And since our velocity is positive, then we can talk about distance as constant, so constant positive velocity. So as long as velocity is constant, and the distance, so the word distance is valid since our velocity is positive. Okay, so thinking about distance is equal to velocity times time, well, then our distance is going to be 4 feet per second times our time. Now, it's actually our change in time. That is a second time. So velocity times a change in time. So our change in time is 3 seconds. So our distance would be 12. The seconds cancel and we're left with feet. So calculation-wise and algebraically, our formula is distance is equal to velocity times change in time. And graphically, we can interpret what Ben in the back said as what Ben in the front says. Okay? Graphically, we can interpret this as, okay, here is a time along the horizontal axis, and then we've got velocity along the vertical axis. And so here we're taking the width. Down here is a change in time of 3 seconds, and a height of 4 feet per second. And so if I multiply these two values, length times width, well, the unit is 12. I'm sorry, the numeric value is 12. And feet per second times seconds, those cancel and we're left with 12 feet. So somehow this area under our function, v of t is equal to 4 feet per second. The area under this function between time t equals 0 and time t equals 3 is 12 feet. Okay, so Jeff, to address your question here about how will this change if our times between t equals -1 second and time t equals 3 seconds. Well, here we're still going to assume that we have 4 feet per second. And so now, if we look at the calculation version, then we would have, for this one, we would have that our distance will be 4 feet per second times, well now our change in time is 4 seconds. And so we have 16 feet. And just to be complete, because I'm actually going to address this in a second, in terms of our interpretation, I still have the exact same picture. I've got a picture where I have velocity as my function, v of t, is equal to 4 feet per second. And now I'm interested in the times between time t equals -1 and time t equals 3. And so that entire area of that rectangle is 16 feet. Okay, so this idea here, as long as our velocity is constant, then both of these ideas totally make sense. And in particular, what I can write down for our first example, we'll call this one A, and then we'll call the second question B here. In part A, I can describe the area under the velocity function between time 0 and 3. I can describe that by writing the integral from 0 to 3 of v of t dt. And this describes, this is our distance traveled by the particle between time t equals 0 and time t is equal to 3 seconds. And so in this particular case, the integral from 0 to 3 of v of t dt is equal to 12 feet. And for part B, the integral from -1 up to 3 of v of t dt is the distance traveled by the particle between time t equals -1 and time t equals 3. And that value is 16 feet. Okay, any questions about that? Okay. All right, then let's look at another example. In our second example, a particle moving along a straight line has velocity given by v of t is equal to t squared minus 7t plus 10. And this is, again, in feet per second. How far has the particle traveled between time t is equal to 0 and t is equal to 2 seconds? I'm sorry?
It's not a constant velocity.
That's exactly right. So our v of t is t squared minus 7t plus 10. And so definitely, at different times, this velocity is going to be very different. Which means that at first glance, this idea of distance equals velocity times time doesn't seem like it's going to be very useful. But don't give up on this too easily. Hold this in the back of your mind. Let's take a look at what this function looks like. If you have your calculator, please pull it out and graph the function v of t is equal to t squared minus 7t plus 10. When you get a picture of this function, it should be a quadratic function, it should be a parabola, and it should be upward facing. So double check where that graph crosses the horizontal axis, in this case the t-axis. So what are the x-intercepts of this graph?
2 and 5.
2 and 5? Okay, do I have a second on those values of 2 and 5, Jennifer? Yeah. Yeah, that was I'm seconding it, not I have a question. Okay, so this is our picture of the function v of t is equal to t squared minus 7t plus 10. And the idea here is that we want to figure out how far the particle has traveled between time t equals 0 and time t is equal to 2. Now, something that I notice about this function, this velocity function, is that from the time of t equals 0 seconds up to the time t is equal to 2 seconds, the velocity, which is this graph right here, is positive. It's above the x-axis. So velocity is positive for this particle, which means that if our particle is traveling along a straight line, here's our straight line, from time t equals 0 to time t equals 2, the particle is moving, if we think of positive as toward the right, the particle is moving in the right direction. If our velocity is negative, that means that our particle is moving to the left. Positive velocity, particle moving to the right. Negative velocity, particle moving to the left. So when I'm interpreting this function here at time t equals 0, the velocity of the particle is positive and very large. So at time t equals 0, the particle is moving really fast. And as we move from time 0 to time 2, the particle continues to move to the right. But that particle is slowing down. The velocity is decreasing. So the particle starts out moving really fast and then slows down until at time t equals 2, the particle stops for a split second. And after that, our velocity is negative, so the particle starts to move back to the left. Okay? Until time t equals 5, at which time the particle moves back over to the right again. Okay, so we'd like to know about the distance that the particle travels between time t is equal to 0 and t is equal to 2 seconds. So all during that time, the particle is moving off to the right, because we know this because our velocity function is above the x-axis. All right, now the idea of distance is equal to velocity times the change in time. Well, this asterisk is really important right here. This is true as long as velocity is constant. Now, our velocity is definitely not constant. Our velocity is curvy, and in particular, it is decreasing. Okay? And so that's our problem. But what we want to do is we want to say, okay, well, even though our velocity is not constant on the interval from 0 to 2, I'm going to pretend that the velocity is constant. I'm going to pretend that over the first second, the velocity is a constant that is exactly the same as the velocity at time t equals 0. And then this area, this rectangle, represents the distance the particle has traveled over that first second. And then I'm going to pretend the velocity is constant over this second interval. And so now I can approximate the distance the particle traveled by calculating the area of the second rectangle. All right, so I can add the areas of those two rectangles together, and it gives me the total distance traveled by the particle. Now that's not a good approximation, because I'm saying, well, let's pretend like our function is not curved and steep here. Let's pretend that our function is flat, just for the sake of pretending. That's not really true. So I could do the same thing. I could break this down into 4 intervals and look at saying, okay, well, our velocity function is constant over the first half second, constant over the second half second, constant over the third half second, and constant over the fourth half second. Calculate the areas of those rectangles and get my distance. Or I could do 8 rectangles, or I could do 16, or 32, and I could have as many rectangles as I want, but the idea is that when those rectangles get small enough, what I'm really doing is finding the area under my velocity function between time t equals 0 and time t equals 2. So the distance that the particle travels between time t equals 0 and time t equals 2 is equal to the area under v of t between t equals 0 and t equals 2. And so if I write this down, I can write this as an integral. The integral from 0 to 2 of v of t dt. So the distance that my particle has traveled is equal to the area under my velocity function between times t equals 0 and t equals 2. Are there questions or comments about that? Okay, well, what if we change this up a little bit? What if we ask about calculating something like the integral from 0 to 6 of v of t dt? Okay? We're changing the question now. So instead of going from 0 to 2 and finding the area under our velocity function from 0 to 2, we're looking at, and let me go ahead and redraw this picture since I've already scribbled all over that one enough. So here's 6, 5, 4, 3, 2, and 1. And so our integral from 0 to 6 of v of t dt, well, if we calculate that, then we need to know the area under our velocity function and above the x-axis. But then we get to this middle part where our velocity function dips below the x-axis. And so that area right there is going to be subtracted off. And then we are going to add on this last area over here, this semi-triangular region over here on the right. So think about what's happening in this interpretation. This area over here is telling us, this first triangular black region here is saying how far has the particle traveled to the right? Okay, whatever that number is. Now here, from time 2 to 5 seconds, particle is moving over to the left. So this red area is telling us, okay, we are going to subtract off this distance. So if we say, okay, our particle started here at this point and moved to the right, however many feet it moves to the right, and here at t equals 2 seconds, particle stops and goes back to the left until time t is equal to 5. So we're subtracting off that distance, and then we're going to add our very last distance, and we're going to end up at time t equals 6. And so in the end, what our integral will give us is it's going to give us a net area, which interprets as a net distance. So our final answer is going to be a number that tells us the net distance the particle has traveled. Okay? So for example, if I stand here and I run all the way down here to the end of the room, and then I come back to exactly where I started, my net distance traveled is 0. I may be a little sweaty and hot and tired, but that doesn't matter because my net distance, I'm back right where I started. Okay? And that's called displacement. And so the integral from 0 to 6 of v of t dt tells us the net distance traveled by the particle between time t is equal to 0 and t is equal to 6. But a better word than net distance is displacement. All right, so if we evaluate the integral from 0 to 6 of v of t dt, it tells us about the change in, it tells us about the displacement of the particle between time 0 and time 6. Something to think about there. We have an integral of velocity, and we get out a displacement, or which is related to position. Velocity back to position. When we were talking about derivatives, if we started with position and we took its derivative, what do we get?
Velocity.
We get velocity. So we're kind of going backwards here. Okay, so one last observation. So when you watched me run across this room and then run back, and I ended up back in the same position that I started with, and I said that my displacement was 0, or my net distance is 0, well, that's true. I've run over here, and then I'm running back, and I'm standing here, and I haven't really gone anywhere, but like I said, I've gotten my exercise for the day. So we may be interested in knowing how far has the particle traveled, what is the distance that the particle has traveled, in which case, I don't want to subtract off this area down below here. I want to add that in. And so if I want the total distance traveled, in other words, not net distance, well, in that case, then I need to make sure that this red area is actually a positive value. And to make that happen, what I need to do is to redraw my picture. Instead of having this portion down here below the x-axis, I'm going to bump it up above. And I'm going to erase that portion down below. And so now, what I'm finding is the area under this new function, where everything that was negative is now positive. And so my total distance traveled is going to be the area between 0 and 6 under our velocity function, but it's not just our velocity function. Our velocity function got bumped above the x-axis. How does that happen? Well, that happens by taking the absolute value of velocity. Bumped above the x-axis. So we put all of our velocities above the x-axis, and then we can add up all those areas and make them all positive. Okay, so one thing that integrals do is that they talk about area, net area, and if the function that we're taking the integral of is a velocity function, then area under the velocity function between two times tells us the displacement of the particle, tells us the net distance the particle has traveled over that time period. Okay, so that's one thing that we might be able to answer. Are there any questions about that? Okay. So on to question number 2. Question number 2 is, how the heck do we evaluate these things? How to evaluate a, and I'm putting in parentheses, definite integral. Eventually we'll be calling these definite integrals. Right now they're just integrals. We're going to talk about another type of integrals called indefinite integrals later. But for now these are integrals. How to evaluate an integral. And this is a theorem. It says if f is continuous on the closed interval from a to b, then the integral from a to b of f of x dx is equal to capital F of b minus capital F of a, where capital F of x is any antiderivative of little f of x. All right. So over here, when we had an integral that was an integral of a velocity function, the output that we got, this integral answers, it says, what is the displacement of the particle? That kind of makes sense over there, because here we've got velocity and we're finding its antiderivative somehow by talking about displacement. And that's what this theorem is saying over here. If you want to evaluate an integral, find an antiderivative of the function in the middle, plug in the top number, plug in the bottom number, and subtract them. Let's look at an example. So our very first example, where we had a constant velocity of 4, we had the integral from 0 to 3 of v of t dt, where v of t was equal to 4 feet per second. So we are evaluating the integral from 0 to 3 of 4 dt. So what our theorem over here says is, I want to find an antiderivative of the function in the middle. So my function in the middle here is 4, and so I ask myself, what function has as its derivative 4? Yeah, 4x plus c. Now, because I have a t on the end here, I know that my variable is going to be a t rather than an x. And so if f of t is equal to 4, then the antiderivative, capital F of t, is equal to 4t. And technically we also have a plus c on the end. right, so what does our theorem say? It says find an antiderivative and then plug in the top number. So f of 3, capital F of 3, which would be 4 times 3 plus c, which is 12, plus c. Plug in the bottom number, f of 0, which is 4 times 0 plus c, which gives us c. And now subtract the two. So the integral from 0 to 3 of 4 dt is equal to capital F of 3 minus capital F of 0. So in our case, that's 12 plus c minus c. We end up with 12. So we looked at the function in the middle. We found an antiderivative. We plugged our top and our bottom numbers into that antiderivative and we subtracted. All right, so let's take a look at this one. Because on this one, we don't have that rectangle shape. So let's look at this one, the integral from 0 to 6 of v of t dt. Integral from 0 to 6, our velocity function was t squared minus 7t plus 10. And then we've got a dt at the end, and we want to evaluate this integral. Okay, so the first thing I'm going to do is that I'm going to look at my function in the middle, and I'm going to find an antiderivative. So we talked about antiderivatives, but man, that was a long time ago, right? That was not the Thursday before Thanksgiving, because that was when we talked about 5.1 and 5.2. Not the Tuesday, because that was our test, but the previous Thursday. So it was a while back. So antiderivatives, well, that's undoing a derivative. So what are we doing here? Well, to find the antiderivative of t squared, I'm going to add 1 to the power and divide by that new power, or multiply by 1 over the new power. In my second term here, I'm going to add 1 to the power here, which is going to give me a t squared, and I'm going to divide the number in front by that new power. So I have 7/2 t squared. And the antiderivative of a constant, I'm asking myself, what function has as its derivative 10? Well, that function is 10t. And then in the end, I've got a plus c on the end. So this is my antiderivative, and here's a bit of notation. I'm going to draw a vertical line, and I'm going to evaluate that antiderivative between 0 and 6. So this says plug in 6, plug in 0, and then subtract. So first I'll plug in the 6, so I've got 1/3 times 6 to the 3rd minus 7/2 times 6 squared plus 10 times 6 plus c minus, I'm going to plug in the 0, the bottom number. So I've got 1/3 times 0 to the 3rd minus 7/2 times 0 squared plus 10 times 0 plus c. All right, so some things that happen here. First of all, I've got a bunch of zeros over here, so I don't care at all about those. And I've got a plus c and then minus a c, and so those will cancel. And in fact, those plus c's are going to cancel every single time. And now I'm left with 1/3 times 6 to the 3rd minus 7/2 times 6 squared plus 10 times 6. And this requires some calculation. So if you have your calculator, please pull it out and do some number crunching. You get 6. Do I have a second on 6? Got a second on 6? Okay. All right, so we end up with a value of 6. Now, originally, when we were talking about the meaning of this integral, this function in the middle here was a velocity function. And the units for the velocity function are feet per second. And we're multiplying that times a little dt, so a little change in time, whose units are seconds. And so that cancels the seconds on the top and the bottom, leaving us with feet. So we're adding up a bunch of feet. When you add up a bunch of feet, you get feet. And so we end up with 6 feet. So this says that our particle, which moved to the right for 2 seconds, and then moved back to the left for seconds 3 through 5, and then back to the right for 1 more second until time 6, the net displacement, or the displacement of that particle, is 6 feet. It doesn't matter how far down I went there. I started here, and when the particle ended, it was 6 feet to the right. All right. Any questions on evaluating that integral? Find the antiderivative, plug in the top number, plug in the bottom number, and subtract. Okay. All right, so let's stop there. So I have a chance to get back to tests. Are there any questions?